So basically, I'm talking about continuous automated defense of a large-scale open research network, actually to rephrase the art and science of dynamic firewalls. So I am Ashish Sharma, and my colleague Craig Leres is here. We are from Lawrence Berkeley National Lab. We are the Department of Energy Research Lab. We are open, unclassified lab. We are not Lawrence Livermore Lab, so it's people generally confuse us with Livermore. We are non-weapons lab. So a little bit about us, pretty much dedicated physical sciences lab. We run all kinds of activity, including like high energy physics, human genome, all kinds of stuff. Name to the fame is actually there are 13 Nobel Prize winners. If you go in cafeteria, there might be a Nobel Prize winner behind you. And then we also comprise for about 3% of the National Academy of Sciences. So it's pretty good. I think the one incentive in the lab to win a Nobel Prize is that you get a dedicated parking spot. So, but here is a little more narrow thing. Berkeley Lab is known for Cuckoo's Egg. That was a fascinating story of like a 36-cent accounting error, which ends up becoming like an international spy episode back in 1988, 89. And then Lab also came up with a few tools like traceroute, libpcap, TCP-dump. Craig actually, in fact, is a original author of TCP-dump. So, and then more recently, Lab is birthplace of Zeek, formerly known as Bro Intrusion Detection System. I'm not sure how many people know of Bro or Zeek, but it's a pretty solid intrusion detection system. And I primarily work on that. So here is the reason we are here is to actually give you like an overview of what problems we are facing. So we are an open research lab. The idea is actually that science comes first, and then security works in conjunction to science. So like there is this all open science, big data, we have it, high-speed networking. So when we talk of big data, we are talking about like petabytes of byte transfers. High-speed networking is like we have multiple 100-gig links going in and out. So be it like CERN in Switzerland, there might be terabytes of data going back and forth, or like there is a new telescope in Chile, you'll get petabytes of data from there. So all kinds of stuff like that. Our guests actually are worldwide. So the way we run our network is that we will have researchers coming from anywhere in the world. They might be in lab for 3 days to like 3 months or a year. The idea is they come in, they run their experiments, they collect the data remotely. So we want them to have all kinds of access. So basically, we do not have a firewall. And reason is that these worldwide collaborations and huge flows are very difficult. So like if I can get a firewall for 100 gig links, I will buy 2, but you really don't get that. So we have to run our network without firewall. And second is that we do not have endpoint security, like centralized management. Like everybody can bring their own devices. And the idea is like if a researcher came to the lab, we don't want him to waste like half a day trying to connect to the network. So people bring their own device by default. So the strategies we use, unlike other networks, is that we go for pervasive visibility. We want to see everything in the network, so that is the way we can actually figure out what's right, what's wrong, what's going on. And Zeek is actually a tool used for that visibility. And another philosophy is that incidents will happen. Let's catch them, let's fix them, and let's make sure that the same incident doesn't happen in the same manner again. So here is a high-level overview of our network. So we have a ESNet, which is our network provider, ISP, Energy Sciences Network. And then we actually have a tap outside our border router and a tap inside the border router. Both places we actually watch for it. Then there is Zeek, which actually goes and talks to something called ACLD. So most of this talk is about this homegrown tool called ACLD, which actually allows us to manipulate ACLs on border router, or null zeros on border router, and that is how we decide that, yeah, this particular connection can come in, or this connection needs to be blocked in. And that is what is our dynamic firewall. So I'm just trying to lay up a little groundwork for ACLD. But so this is a very high-level overview, but the further you go down, so it's not only that we have taps, internal and outer, we actually even have taps inside our subnets, and not only is like Zeek involved, but we actually do net flow analysis, sys logs, Windows logs, and all kinds of things. But everything ultimately ends up talking with ACLD and making a block. And the way we have designed our network is like there is a network layer, then we put bunch of monitors, and then there are controls which get into the place. And controls is what decides like who can come inside the network and who cannot. And and that's how we do our firewalling. So I picked up this particular specific scan reconnaissance detection because this actually is a big chunk of our blocks so we use various strategies, and this is where like art and science get interesting. So like we use simple summary statistics where it's like, okay, if you touch 10 IPs in T amount of time, you get blocked, or signature based, or there are behavior based detections too. Like for example, you run Nmap by default, Nmap does port 80, 443, and ICMP. So if that behavior is seen, our intrusion detection system understands that, yeah, this is an Nmap scan, let's block them. Then there are probabilistic models like threshold random walk. There's a paper actually from Vern Paxson and his team, and this actually uses hypothesis testing where we can actually find badness within like 3 to 4 connections. So there is this hypothesis like, okay, yeah, this is a good connection, bad connection, good connection. By a third or fourth connection, we would know. And then, of course, know your network approach where we use strategies like knock-knock, where it's like, you go to your home, you know that how you can enter your home if you forgot a key. Like there is a window or a back door. But if I come, I don't know. So I'm knocking on all the windows or I'm trying each door, and it's like, this guy doesn't live here. So that's why, like, if somebody knows their network, they know this is my Sophos server or this is my Windows server. But a bad guy is going to be like, oh yeah, let me probe. Is this machine a Windows server? Is this machine a Windows server? Or is it so that kind of strategy or landmine is what we use. But here actually comes the fundamental problem, and that's where the ACLD gets involved. So this is like 5 years of data. We have 20, 30 years of data. But see, back in 2014, we would block about 50,000 IP addresses at a given point of time. And this is where equilibrium used to be. And then over a period of time, we ended up blocking like 200,000, 300,000, a million. So the problem coming to us is that the badness on internet is increasing. This is not a finding, this is of course. But we still need to keep our network open. We still need to keep bad guys out. So let me just zoom in a little bit here. So here is the deal. Like, see, this is just last 1 year. We generally are hovering about 600,000 IP addresses at given point of time, which we will be blocking. So, but here are these spikes which actually go down. And these are where we actually free up all the blocks so that we can actually have enough budget to start blocking again. Because the things go crazy. Like this is about a week where you would end up blocking. So, yeah? Right, yeah, so we have, right now we actually get about $1 million in budget with networking group. We have asked them to give us like 5 million, and they're like, so that is where, and I think that's where we are going. We are actually thinking about like billion budget, and that's where we will be scaling with ACLD. So this is Juniper. Good idea, because yes, we are doing that. So, so here are the controls. Like initially, the ACL blocks were 10,000, and this was great in 2010. But then we started like all these botnets keep coming in, all these scanners and security researchers actually like they start probing your network, and then we went for BGP null routes. But then there is this. So this was pretty much scientific. Like, yeah, here is your budget, here is your block. We started using strategies like catch and release, where we would say, okay, here's this IP, this is bad, let's block it. That IP hasn't bothered us for another 6 hours or 1 day or 7 days, let's release it, but keep a memory of it so that if they come back again, we don't use a threshold, we block them at the very next connection. And that way we were able to actually expand our budget to about 10 million. That's not enough either. So there was subnet level block where we would compress and we would block /24/25 and so on and so forth. And then like Marai came up, and then it was almost like a crazy day because you would have 500,000 IP addresses which would scan you overnight. So we came up with something called TCP SYN flag block, where we would block a specific port But the way it gets blocked is like if you put a normal block, then if that port becomes a source port, that is a valid connection that could also get blocked. So the SYN flag blocking allows you only to block a particular connection on a port if it's a SYN packet coming in. And that actually allows us to like weed off 500,000 to a million IP addresses without bothering. And the way we do this is that Zeek or Bro actually is smart enough to understand. It keeps a count of each port per IP address. Oh, sorry, how many IP addresses are scanning for a particular port. If that threshold crosses 50,000, for example, it would move from like IP level blocking and go and apply SYN port block into the border, and then wait for a decay. And when the decay happens, then all of a sudden it would actually remove the SYN port block and then go back to IP-based blocking. So these were some strategies. But here is the, so let me set up a stage for where ACLD gets into the action. So Zeek is our intrusion detection system. It does all these kinds of heuristics, uses a API which we call broker or a net control framework, and that is what actually goes and talks to ACLD, which actually would start deciding like, okay, what network equipment it should be talking to, because over a period of time we talked about we blocked on Force10, we blocked on Cisco, we blocked on Juniper. So ACLD makes these things transparent. Let me just invite Greg to actually talk about that one.
Thanks. So probably you guys are asking yourselves, well, what is ACLD? It's a daemon that we use to manage router resources. Originally, it would just deal with access control lists, but later we added null zero routes, and there's a bunch of other things that got added. The initial motivation for ACLD was that we got permission from the networking group to be able to have Bro have the ability to add blocks to the network through an API, which was pretty cool. One of the network engineers that was in LBLNet at the time wrote a proof of concept that was in Perl, and that actually worked, and we thought, wow, this is really cool. But it was very slow because the way that it was implemented, it would log into the router, make a change, and then log out again. And it turns out it's really bad if it takes a long time to do a block. What you ideally want to do is have Bro identify an address and then have that address stop being able to do business as soon as possible. Because the longer that it can keep on doing things, you know, the bad things can happen. Anyway, in about 2002, I started working on ACLD. So there were a bunch of design goals I had when I started out, and number one was low latency. I want the thing to be able to implement the changes as quickly as possible, so I try and do everything else that I can to make that happen. I want a persistent connection from ACLD to the router. I want a persistent connection from Bro to ACLD. I'd like to be able to add support for new routers with, you know, minimal effort. IPv6 is a must because we were an early adopter of IPv6, and it's a lot easier to just bake it in from the beginning. And then we need audit logs. The API is designed to avoid a request response delay. So basically, the client can just stream requests and then eventually get back an answer. The router support is done using the expect language, which, if you guys aren't familiar with it, it's a neat language that you can use to automate command line tools, things that are normally interactive. Each request that goes to ACLD has a cookie, which is a numeric value, and all of the replies come back with the matching cookie. So that way, if you stream 10 or 100 or 1,000 requests, you can match up the responses and find out, oh, 3 of these didn't work for some reason, and then maybe you know, take some action based on that. And then I also used expect for the initial command line tool, and that's what Bro used for a number of years, even though originally I had hoped that Bro would communicate with ACLD directly because that would lower the latency. Here's the expect architecture in a block diagram. So you can see it just pretty much as you expect. Bro talks to ACLD. ACLD forks a child that runs the expect interpreter. It would do something like run telnet back in the day, or later SSH, and eventually connect to the router. A little bit of history. In the beginning, we had Cisco and Force10. I think we actually transitioned from a Cisco on our border to Force10, And so I ended up writing expect scripts for both of them. Later, when we started getting into the null zero business, I wrote some native code to add FreeBSD routes to the routing table. Um, and, oh, I guess actually IPFW and PF. So kind of as an experiment and to use in a couple weird cases, had the ability, so you could do ACLD and you could do blocks that would actually throw in access list changes on your FreeBSD box. And then at some point we got an appliance from CPacket called or actually, yeah, it was from CForce. It was a 10 gig blocking appliance, and they gave us a shared library. They gave an API to be able to add and remove blocks. So that was for the duration that our wide area network was connected at 10 gigabits. That was our method for doing blocks. 2012, we started getting into Juniper routers on the border, and so I wrote C code to be able to access the firewall rules in the config. This is using libxml and libssh2. That works pretty well, except that commits, if any of you are familiar with Junipers, takes tens of seconds, and so it's totally not suitable for intrusion detection blocks. Null zero came in 2013. I guess I got ahead of myself a couple slides ago, and this is done natively in C code. It can add, remove, and list routes. Works pretty well. We've been running with this, well, ever since then. And then once the route gets installed in the local FreeBSD kernel, we use something like Quagga or Bird to advertise the routes to the routers. One thing about it is we can actually advertise to both routers because we have two wide area. This thing has a button on it someplace. We have a couple wide area routers. And this comes handy because it means that if one of the ACLDs goes down, the other one can keep up the shields on both boxes. Let me breeze through some quick examples about how to talk to ACLD. I actually was using Telnet when I was developing it. When you first connect to it, you get back a response that tells you a Unix timestamp, a sequence number, the verb that was executed, and then optionally there's a dash on the end of the line that says there's a payload or a comment associated with this, and it just has lines of text and then a dot on a line by itself. So here I might want to add a null zero for a particular IP address. My cookie is 803. I had a comment that I added with it, and it was successful because I got back an answer, and it gave me, it basically echoed the verb that I put in. If I try and add it again, it's going to succeed because at the end the null zero is still there, but it's going to tell me in a comment that, by the way, you already had blocked that guy. Then if I want to remove it, it's pretty simple. It looks pretty much like it was when I added, except this example doesn't have a comment. If I try and remove it again, that's going to actually fail because it didn't exist. And it's going to give me a little bit of information about why it was unable to complete that. Now we're into more recent things. One of them that was pretty important was adding this feature that I call replicant after Blade Runner. And the point of that is to have two different ACLDs that keep in sync with each other. So what happens is you give a request to one of them, it sends that request to the other one, and now if everything's up and running, they all have everything in sync. If one of them happens to be down and you change an ACL, it's going to get out of sync, but normally ACLs are sort of done interactively. They're not really done automatically by Bro, certainly. And as I pointed out before, if one of the ACLDs is up, then it's advertising routes to both of the border routers. So that means I can take down an ACLD box to do maintenance. It can fail. All kinds of things can happen, but we're able to add and remove null zero blocks. Let's see, what else? Re-implemented the CLI script in Python. That let me do some neat things. For example, it tries to connect to all the ACLDs that it knows about, and whichever one connects first is the one that it does transactions with, which means if one of the boxes is down, you don't really notice. There's no additional latency. It talks to the other one. Sheesh mentioned the TCP SYN flags. It was pretty easy for me to add code to that to make it so that Bro or a network or a security engineer could go in and add a port block for port, you name it. So the stuff we're working on now is we'd like to have Bro natively talk to, natively speak the net control protocol, because we would like to cut out that process that sits in between Bro and ACLD right now, because we want to get the latency down. I think there's probably request response delays that get introduced because of that. So there might be some milliseconds we could cut out. We'd also like to have some attention to both speed and scale. We'd like to lower the latency to implement a change down to like tens of milliseconds. Right now it varies quite a bit due to the fact that the routing protocols get involved, and sometimes OSPF or BGP, they decide to like consolidate some stuff or do some garbage collection or who knows what, and the delays kind of go up. Got a question? The question is about using some network cards to maybe do the blocking. The problem is that we have multiple 100 gig interfaces at the border. No, I don't think it's the speed of the NIC that it comes down to. Usually, it's the stuff that happens kind of after ACLD. And let's see, the other thing we'd like to do is scale ACLD, give us a much bigger blocking budget, billions of IPv4 addresses. The other thing is, in the past we had a dedicated blocking device, and we kind of like that because it takes some constraints off of our choices on wide area routers. We don't necessarily have to have one that has the ability to do 10 million or 100 million routes. The network group likes it if we have a separate box. And I think that's, we're ready to field questions. If you guys have anything else in addition. I see one right here. So there's a question about safety checks. When this first came up, well, actually, when we got permission to do auto blocks, a whitelist was one of the requirements that the head of network operations put on me. And so there's been a whitelist in ACLD from the beginning. I feel that really Bro should be smart enough to have its own whitelist, and in fact, it does. So we kind of have both, and things that are really important are on both lists.
We kind of use multiple different strategies as well for safety. For example, Bro allows us to keep a state of like every remote IP we have actually established connection from our side. Bro would actually keep that in a Bloom filter in memory. So if we are blocking it, so it's like, why am I blocking an IP which internal machine has talked to? And that would actually pop up on the scale. Likewise, what we have done is that we have this huge list of subnets which are research and education networks. So if they get blocked, we actually eyeball those things too. And then we have made things very easy for our community, like user community, to go and check if they actually got blocked. If they are, then we will immediately take. So there is a portal which is local to the lab and remotely, so that you can easily find yours if you have been blocked. If you have any other questions, you can feel free to like send us an email or security@lbl, much easier than our names. And we would definitely like to hear more feedback or any other ideas you have. And thanks for having a talk here. This is a fantastic conference. This is first time we came here, but I think this is not the last time we'll be here. Thank you very much.